So I have the pleasure of presenting Dr. Hauer. He is an assistant professor of sociology at Florida State University. His expertise is at the intersection of demography, migration, population projections, and climate change. And actually, recently, one of his research has been focused on how migration induced by sea level rise could reshape the U.S. population distribution. And this has been featured in a lot of media outlets. Before coming to Florida State University, Dr. Hauer spent 8 years directing the Applied Demography Program at the University of Georgia, where he provided valuable demographic research to local, state, and federal governments. So please join me in welcoming Dr. Howard to our brown bag.
Thank you. Um, Thanks for having me. It's really cool to be here to be here virtually at Berkeley. There's a lot of people here who's I'm very familiar with all of their work, but I've never actually had a chance necessarily to meet. So it's really cool to be here. I'm going to be presenting some work today that's sort of emerging. This is a preliminary kind of work. It's unpublished, so any kind of comments, questions, refinements, advice would be really cool to take in here and incorporate. So this paper is really around three different concepts, and the one that sort of is the anomaly, to not use a pun, is the anomaly right here, demographic anomalies. Most of us are at least familiar with big data, and we're becoming, if we aren't, we're becoming increasingly familiar with causal inference as well, but maybe less so around anomalies. I'm also my co-author on this is Stephanie Bohan at University of Tennessee, where she gave a talk a few years ago when she was president of the Southern Demographic Association. It was on the fringe of some of these concepts. So what do I mean by anomaly? Maybe in the last year, you saw headlines like this. I hope, or saw this was all over the news, as you can see at the latter half of 2020. They found this weird monolith. Some of them were calling it an anomaly, a geological anomaly that had randomly appeared in the Utah desert, and they were, hiding the location of this monolith, some sort of viral marketing campaign. And when I refer to an anomaly, I'm not talking about this kind of anomaly at all. I'm really referring to statistical anomalies in our demographic data. So again, the three like themes in this talk, in this paper, are around causal inference, big data, and then what might be less familiar as well as abductive reasoning. That's where bringing all three these together gets us our anomalies. So if you're unfamiliar with causal inference, this is how we're looking for the underlying mechanisms behind the effects that we detect in any kind of social data. And we traditionally use this through RCTs, randomized controlled trials, or natural experiments. And the most basic framework for causal inference is just you have an outcome where you have treatment, and you have an outcome where you have a control. And the difference between those two is typically the causal effect, or what you would infer to be the causal effect. And this is how medicine is done. This is where we're increasingly moving in terms of social science. But unfortunately, these RCTs can be incredibly expensive to actually run, and they might even be completely infeasible to run as well, to actually detect a causal mechanism. This was a tweet from, well, God, it feels like forever ago, or when you look at the date, but seems so recent. This was a discussion about the cost of implementing an RCT as a graduate student. So here we have a scholar talking about, as a grad student, doing an RCT for about $100,000, just under $100,000 as a graduate student. And they were looking up, nets or whatever was the effect. And the response on Twitter to this was lukewarm, I guess would be a nice way of putting it, as some of the responses were sort of like $100,000. Wow, that would be amazing. My whole dissertation research was for 21,000 between 9 different grants. And I love this one, the reply, which is, I won a $5,000 travel grant for field work, and that was quite the treat. So RCTs, in terms of getting to a causal effect is not always feasible simply because of the cost. It can be really expensive. So it's in some cases, it's prohibitively expensive. The real world is also pretty messy. And so implementing an RCT can be impossible in some cases. Like, how do you do a randomized controlled trial for country level austerity measures, for instance, right? There's ethical considerations between being able to deploy RCTs. And in demography, we're already swimming with data oftentimes. And so getting an RCT for secondary data users like us can be not necessarily up our alley. The alternative, of course, is natural experiments. These are much cheaper, but oftentimes they require expert knowledge of the situation, where you sort of look after the fact to determine what might have happened between two different groups. And this is where we start to get a lot more synthetic cohort type measures. So here's an example. This one was in PLOS One. This is Stuart Geidel-Bastian's paper and colleagues, where they were looking at the effect of the one-child policy and the later, longer, fewer policies in China from 1973, as well as in 1979, and sort of what is the counterfactual? What would TFR have been had there not been these fertility policies? And the difference between these, in this case, the shaded red is what they used, and the shaded green were the causal effect that they were getting through. And these sort of natural experiments are becoming really, when we started writing this paper, weren't as much in vogue, but with COVID, these are all over the place, these sort of counterfactual estimates of what might have been the mortality in 2020 if we had not had a global pandemic. And so you get these nice little shaded regions with the observed value above it, the observed mortality, and then what it would have been as a counterfactual had there not been a treatment of COVID-19. So these are becoming more frequent in the way that they were applied, and thinking through these sort of what ifs kind of scenarios. Great one to show how this flows right into abductive reasoning was a classic paper by Inev and colleagues in 2015, where they were trying to estimate the effect of an auction starting price on the outcome of the auction. So the final sale price, as well as the probability of the sale. And they found this amazing data set of 31 eBay listings from the exact same seller of the exact same golf club, but the only differences were the starting price. And so I'm going to use INEV to frame abductive reasoning, because causal inference, as it's largely practiced, still relies on deductive reasoning. You have a theory, you pose a hypothesis, you make an observation, and then you either confirm or you don't confirm your hypothesis, right? This is classic hypothesis testing. So in INEV, right, they had, I can't remember the exact theory that they had, but their hypothesis was that starting price impacts the final sales price. They made an observation with their eBay sellers, and then, hey, they confirmed it. That it turns out that, yeah, starting price actually impacts the final sales price of an item. They actually found evidence of this. So here's causal inference in action through deductive reasoning. In demography, this is real classic as well. All of us should be familiar with this type of map. This is John Snow's map from the London cholera outbreak. And he hypothesized that cholera was waterborne. He deduced there was a bad water pump was responsible. And then we have essentially, modern public health gets kind of born out of it. So this has a long history in science. It's most hypothesis testing in the social sciences, and it still follows, right, this type of logical reasoning when we apply causal inference. We have the flip of deductive reasoning, which is inductive reasoning. This is directionally opposite, in which case we start with an observation, we make a theory and hypothesis, and then we confirm whether or not our theory or hypothesis was correct. In demography, there's a famous example of this, and I've got the mortality curve pulled up here on the top right, the differences in mortality rates between non-Hispanic Black, non-Hispanic White, and whites in the Hispanics in the United States. So we start with an observation in 1986 that US Hispanic mortality is better than expected given the socioeconomic status of Latinos in the US. And it births a number of hypotheses: salmon bias, acculturation, healthy migrant. And then we have studies that come out that confirm that these individual hypotheses and these theories are correct, and that disprove these individually theories are also correct. So there's evidence that goes both ways. So generally, when we use inductive reasoning, we're limited to something that we can either prove or disprove, and it's still related to um, um, inductive reasoning as well. It's just sort of the opposite. The last one, the last sort of logic system that we have in science is abductive reasoning, which is more similar to inductive reasoning, which is to infer the cause from the effect. And this allows a scientist to move between deduction and induction without necessarily having a strict hypothesis testing regime. So, but it can be sort of worked with all of these. It helps you find the pattern, right? You find something and you go, why is this happening? Why did we find this effect? Suggest some sort of hypothesis. Deduction helps us build a testable hypothesis, and then induction gives us the empirical support. The classic example that people use for abductive reasoning is an old one as well in the sciences. Back in 1846, astronomers made an observation that Uranus's orbit deviated from its predictive path. That's also the pattern. They make a hypothesis that another body is interfering with its orbit, and then they discover the eighth planet, Neptune. In the physical sciences, this sort of this framework is being used increasingly, especially as sort of the physical sciences get increasingly esoteric. LIGO, the gravitational wave observatory, uses this now. This was a burst earlier in 2020 where they detected an anomaly for a gravitational wave burst in part of the sky. And immediately astronomers sort of rushed out to figure out what was causing this. They have an effect. They don't know what it is. It's in the same general area of the sky as Betelgeuse. And so we've got these great tweets from these astronomers who are all excited and giddy about gravitational waves, talking about, well, I know it's not, Betelgeuse didn't go supernova. I know that didn't happen. It's nothing, but they're still all going to check. And you've got competing scientists saying, well, no, it's not going to be it. Here's why it can't be Betelgeuse that blew up. This is not necessarily a testable hypothesis in this framework, right? You can sort of look and say it did or it didn't, but there's not enough evidence for you to actually sort of come out and say, now we kind of know Betelgeuse didn't blow up. But in the actual moment, they're trying to reason through what is the most likely explanation for this anomaly. And I think in this case, it actually was a true anomaly. The false alarm rate, this was one of them. So that's abductive reasoning. And in demography, we can use these causal inference techniques with abductive reasoning because we have so much data. It allows us to really deploy causal inference in a manner that we haven't really seen, right? We don't necessarily have to do RCTs, and we don't necessarily have to have expert knowledge of a natural experiment to actually deploy some of these. We can sift through the reams of data that we have to try and find true actual events. And demographic data is an ideal big data environment for this, right? We're some of the original big data scientists to latch on to, sort of a sexy term. So this is what we use. We combine causal inference, abductive reasoning, and demographic data on mortality and fertility data in the US to identify potentially anomalous demographic behavior. So we're really looking for the hidden baby booms and busts and the hidden mortality spikes and dips in the United States over the last 20 years. And it's a lot of data, and we don't necessarily know the causes of these hidden effects, right? These hidden anomalies. So what we're really doing is we're trying to identify effects without the knowledge of the cause. So can there be a cause that is so large enough to cause an effect that we don't really know what's driving it? And to do this, we use a time series outlier detection algorithm from the early 90s, and it's implemented in R via the TS outliers package. This is now, I believe this algorithm is now native in one of Ram Hidman's packages in R, and it's also native in one of the EpiStats programs to look for outliers. In a real quick nutshell, the way that the algorithm works is it fits the best fit ARIMA model to a time series, and then it looks at the residuals to look for their significance to identify potential outliers, potential anomalies in the data above a critical threshold. The Chen and Liu suggests 3.5 as the significance level, is the critical value. It then refits the ARIMA model with those time points removed, with those observation removed. So sort of fitting what the counterfactual should have been. And then it goes back and it re-estimates the ARIMA. It does this iteratively over and over again until there's no additional anomalies that are detected. And the really cool thing about this approach is it identifies, not only do you sort of, you can run this on almost any time series as long as you have enough time steps. You can tune the sensitivity of the model, but you also identify different types of anomalies, different types of outliers. There's 3 different outliers that get detected. There's additive, a level shift, and a temporary change. And additive is one single time period, right? This is sort of like a one-time thing. It affects one time period, like um, um, a single event, like maybe a mortality event, maybe it's a fertility event, something that happens in one time period. A level shift is a permanent change that occurs over multiple time periods, right? You can imagine a time series shifting because of some sort of effect, higher or lower. That would be a level shift. And a temporary change is a level shift that, or an outlier that lingers over multiple time periods before decaying. So you might find a temporary change that has sort of lingering effects afterwards. 3.5 minimizes type 1 errors or false positives. So here's an example. I'll give an example of how this works. It's not a demography example, but I think it illustrates it very well because we also have a very clear causal effect. So for a very long time, the Swiss bank pegged the exchange rate between the Swiss franc and the euro at 1.2. So it was always at 1.2 on purpose, right? It traded at 1.2 euros per Swiss franc. And then inexplicably, on January 15th, 2015, the bank removed the currency peg and it allowed the two currencies to trade freely. So if you can imagine a counterfactual, what would you imagine the exchange rate of the euro and the franc to have been on January 15th had they not removed the peg? You would have imagined it to be 1.2. Right? I mean, that's what it would have been. That's what the policy was in place. This is how the currencies then traded, right? So immediately there was, you can see a lot more noise in the time series and so on that occurs without the peg. If we run our outlier detection algorithm on this, it detects an anomaly exactly where we'd expect it to do. The counterfactual, if you were to remove that point, you end up with essentially a flat in terms of what it is. And the difference between these is a t-score of 144. So this is an extremely significant effect of a level shift on the Swiss exchange rates. So, but the general idea is you have a time series, you fit an ARIMA model to it, you search for the residuals that are very large, you remove them, you refit in an iterative fashion, and it's the difference between the counterfactual and the observed value that we end up creating, estimating as our causal effect. In this case, you could see the causal effect is about 0.2 euros per franc in a difference. So I'm going to pause here real quick for questions about the algorithm before I start showing, or even the approach before I start showing actual results.
So we have a couple of questions. One was in a private text to me, a direct message about distinction between measurement error and real phenomena. Related is Aisha's question without it. Well, let's do that first, then we'll do Aisha's question.
Yeah, so so measurement error can definitely come in. There's also spurious outliers that could also pop up. I'll show the robustness check in a second, the false positive and false negative rates. But with a critical value of 3.5, we really limit the spurious ones from popping up. Right, that's 3. We're looking at a really large t-score in those cases. And some of them end up becoming even larger, right? Like as you just saw in this one, the t-score was 144, which is just ludicrously large in the case of the Swiss franc. So this is I think we do end up with spurious ones that we pick up. Like it's impossible not to. It's just that we're with as we move that bar higher, as we look for a higher critical values, we're limiting the potential of spurious findings.
Okay, and then Aisha is asking, deeper question here. Without a theoretical expectation, how do we know if an anomaly is actually interesting, worth investigating? Or should we determine that based on the size? Is it the t-stat that tells us whether it's worth looking at, or how do you choose?
Yeah, I think it's a combination of both. And I'll show later as well how we don't necessarily even need to do this when we start clustering anomalies. And it might be really the fact that we have anomalies that are common across time series that becomes important or significant or important, right? That's what we're looking for. Otherwise, I don't know. That's the thing, is we don't know. Some of these are going to be important on some level, and some of them are going to be more than others. That's the determination afterwards, right? That we find that you would make. Either I might find something interesting too and important. Somebody else might not find it nearly as important or interesting.
Okay, and then I have one more question just about multiple comparisons and the length of the time series. Do you want to change the t-stat threshold depending on how long the time series is? Because you're looking at more potential, there's more potential for just a random high t-stat, or do you just use the same threshold no matter what? Or is this a technical issue that is not really worth talking about now?
Yeah, I mean, I think changing the t-stat it depends on the noisiness of the time series more than anything. The more I work in this, the more I find that noisier time series end up pulling in more anomalies than more stable time series. The more time steps, though, the better. The algorithm fits much better. So I'm using mortality and fertility data on a monthly basis. We can't use migration because migration in the US is annual, and we just don't have enough time steps for it. Everything basically turns into an anomaly every time step. It's really weird to watch.
Okay.
So maybe, yeah, higher thresholds, more time steps would be great. Sometimes less, depending if it's really noisy.
Great. Okay, so I think those were all for. I think we'll get a whole new series of questions, or maybe the same questions that we're getting can be rephrased once we've seen some of your demographic applications. So let's go to that.
So we did a robustness check on this. We ran 2 simulations to determine, false positive and false negative rates. We just simulated 1,000 white noise time series that have 180 time steps. That's the length that we have for our data. And we don't introduce any anomalies in this, right? So this is just straight up white noise. So if we detect any anomalies in here, they're essentially spurious anomalies, right? These are false positives. They shouldn't really be anomalies because it's white noise. And out of the 180,000 candidate time steps, we detect 208 anomalies for a false positive error rate of just under just over 0.1%. So I think this is a pretty good. We're not trading too much. I get specificity and sensitivity backwards all the time. We're not trading too much for having a critical value of 3.5. Then we simulated another 1,000, again, white noise time series, same length, but we introduced a single anomaly of the same magnitude at the same time point in each time series. So if we fail to detect this anomaly, then that would be considered a false negative. And so out of the 1,000 candidate time series, we detect 817 anomalies at this time point. And so we end up with a false negative error rate of about 18%. So it gives us statistical power of just under 82%. So I feel pretty good about using a critical value of 3.5 on a time series like what we have for their length and so on. So I feel good about what our findings are. That we're detecting, we're not too restrictive, but not too liberal. So we search for anomalies using monthly fertility and mortality data, using CDC Wonder, 50 states plus DC. It gives us 20,000 state months worth of data. And I'm going to show results where we have I'll show some results for fertility, for mortality, and then some interesting ones that we don't necessarily have explanations for. These are anomalies that the algorithm, what I'm going to show are anomalies that the algorithm is detecting that I think we have a plausible explanation for. So these might be exciting only in the fact that we kind of know what caused them, as opposed to the ones that we don't know, right? The known knowns versus the known unknowns. So here is Louisiana. This is fertility for Louisiana. On the graph up top in the blue, that's the adjusted value. The blue and the gray being the original data, that's Y versus Y hat. Where there is no overlap, so you just see blue, that's where we're not finding any statistical anomalies in here. And so what we find in August of 2005, and then again in October of 2005, two temporary change anomalies that are rather significant. There are 5 t-scores of -5 and -6, which amount to about 4,400 fewer births in Louisiana than we would have expected had whatever happened in August of 2005 and October of 2005 not actually occurred. So this should be relatively obvious. There was a big event in Louisiana in the fall of 2005. It was a national event, right? Hurricane Katrina is what hit Louisiana. And so there's 4,400 fewer births compared to the counterfactual that we would have seen otherwise. This is what Nathan Seltzer and Jenna Nobles were looking at as well. So I find the same thing using a completely different algorithm, the missing births in Hurricane Katrina. So I think this is suggestive that the algorithm is doing what we would expect it to do. It's detecting anomalies that we have plausible explanations for. In this case, in fertility, we've got Hurricane Katrina. This would be an event.
Could you just walk us through a little bit more detail on this example? Why is there no September point? And why does it look like in the red chart at the bottom, there are lots and lots of months that are different from would be predicted?
Yeah, so the points are the onset of the anomaly. And so every subsequent one afterwards, it gets attributable back to the beginning of it. So in this case, when you remove August of 2005, it changes the time series for everything else. It's a temporary change. So it has that lingering effect. And then again, in October, there's another one. If you remove that one later as well, it also has an effect. So you can detect multiple anomalies within the same time period, and you can detect overlapping anomalies as well. The algorithm tries to treat that by only taking the most significant algorithm or the most significant anomaly and the first one, the one that's earliest in the time series. And so you can see those additional months before we sort of go back to normal, the lingering effect of Hurricane Katrina on fertility in Louisiana. So this is not an additive. I'll show an additive later where it just affects one time period. So on the bottom, this tells us the magnitude of the effect. In this case, the lowest month was right around 1,000 fewer births in October of 2005. Does that help?
Yeah, but the curve on the bottom, the red curve, is not just the difference between the gray curve and the blue curve. It's the time series kind of like this gradual return to normal is because that's partly the time series model. That's not that if I did the difference between the blue and the gray, it would equal exactly that red line, right?
Yeah, exactly. Yeah, when you aggregate the difference, you get 4,400, right? That's the full area under the curve, or the full area between them. But the t-score refers to only the actual point.
Thanks.
Here's a different one. This is Connecticut. This is also fertility. In this case, we detect a level shift, a change in the underlying time series. That's the gray being much lower than the blue. That occurs in August of 2009. And it still is pretty significant. It's almost 4, t-score is almost 4, 3.7. And then so what we detect starting there is about 285 fewer births in Connecticut per month than we would have expected otherwise, which over the course of the time series is about 28,000 fewer births in Connecticut than otherwise, or almost 10% fewer births. In this one, we went back and forth to try and think of what might be a potential reason for fertility in Connecticut to drop beginning in August of 2009. And what we believe this is attributable to, in some part at least, is the largest single day loss of the Dow Jones that occurred 11 months before the change in the level shift, right? So we think that this anomaly is linked to the stock market crash of September 2008. There's a number of, the financial markets and people who work in financial services in Connecticut is rather large. And so we think that this is related. If you think it takes about 9 months to have a kid and maybe a few months to adjust fertility behavior, 11 months almost on the dot seems directly where it would be attributable to it. So we think that this is but we don't really know. This one isn't as clear cut as what we might have expected in the case of Hurricane Katrina. So these are two examples in fertility where I think we have a plausible explanation, right? The level shift in because of Katrina, and then of course because of the stock market. Here's a mortality one. This is in New Hampshire. We detect two level shifts to increasing mortality versus a counterfactual, starting in 2010 and then again in 2014, where we have about 8,000 more deaths than expected over the time period. And we think that this is related to the opioid crisis. New Hampshire has the second highest opioid-related mortality in the US, and we know that it actually got worse in 2015, in early 2015 in New Hampshire. And it lines up pretty close to what we're finding here, the additional mortality beginning again in just before then, in November of 2014. So we think we've got the opioid mortality. And then we have what is a noisier time series, one with a lot more outliers for mortality, and that's New York. In New York, we detect 7 anomalies, including ones in opposing directions. So we detect a level shift toward lower mortality amid both additive, which are the individual spikes like buildings, as well as the temporary change within the lower shift. But the one I want to talk about here is this anomaly right there. This is in September of 2001. We get a t-score. That should be 2001. Sorry, a t-score of just over 6. 1,600 more deaths. This would be the effect of September the 11th on mortality in New York. Right here, we find it. It's detectable. It seems exactly what we would hope to find, right, when looking at this kind of model. But I want to point out this one in February of 2004, which we don't actually have a reason for. There's about 144,000 fewer deaths in New York when you remove that time period than otherwise, or about 7% fewer deaths over the time series. And we don't really have a reason why this happened. There was a policy effect for an outdoor smoking ban that went into effect just before this level shift in New York that it seems plausible as a reason that's driving this, or this could just be an anomaly, though it's a rather significant anomaly given its t-score. We do have other results that I think are really interesting. This one is this is an additive outlier. This is Hawaii. It's one single anomaly. In May of 2014, that month, there were 15% more births than we would have expected given the time series. And it's actually the second most births on record for the time series, which is very curious that it flags this month as opposed to any of the others. Why? Why is this the second highest monthly births? Why is this so much higher than a counterfactual would have been? What the expected value when you remove this point? We don't know. This could be a spurious. This could totally be a spurious anomaly. It could be a keystroke error. It could be a data entry error as well. We don't know. We don't have any good reason as to why. And even if it is a spurious or if it is a data entry error in Hawaii, it's one that's uncorrected and is still in there. If there was the true value is somehow different or less in that month, we don't really have a reason as to why it's happening. And then the last one that's interesting is Ohio. This is also mortality. Again, you can see there's a number of spikes. Most of these are in winter time where we see mortality that is a bit higher. But I want to point out this one in May of 2014, where there's 40,000 fewer deaths, or about 1,100 fewer deaths than expected in Ohio, than the counterfactual would suggest. And this is the single largest level shift among all the states for mortality. So what happened in May of 2014 to drive such a reduction in mortality? What happened in Ohio? We don't know. I don't have a good reason as to why. This again could be truly spurious, or it could be that somebody who knows about mortality in Ohio would say, I know exactly what this is. Here's what happened in Ohio. Maybe they put in some kind of policy. I don't know.
We have a question about from Monica. Maybe this would be a place to ask it about trends. So in the Connecticut example, for example, and I think in another one, seemed like the trend changed a little bit. And here, maybe it seems like the opposite. It seems like the gray lines have no trend change, but your blue lines do have a trend change. Could you explain when the difference between a one-time anomaly and a long-term change, and also about these trends?
Yeah, so if that time point is removed and the refit ARIMA has a number of large residuals that happen in the time period after them, then the algorithm would conclude that's a level shift, right? And so that's how it's identifying basically the difference between level shift, temporary change, and additive outliers. So it depends on how long the residuals under the new model remain. In this case, they remained for, the algorithm saw them remaining is for a number of time periods. And so that's why we have, it's a level shift. I have some examples later on if we have time, I don't know, or I could zip to them, that show that the sort of nonlinearity that doesn't get picked up in the level shift in other time series. Or you can even see it in here in Hawaii, where it's very nonlinear and it doesn't detect a level change or a level shift in the decreasing fertility from about 2008 onwards in Hawaii.
Does that answer your question, Monica? Okay, Monica's typing yes. Okay, but I guess I'm looking at this picture. I'm not understanding why the blue line is what is predicted from the model. Is that right?
Mm-hmm. Yes.
Why does the model predict this big increase when the gray line doesn't increase that much?
I don't know. I don't know. I could go back through the model parameters and try and investigate much deeper. This is one of the downsides of having 102 models, right? And trying to sift through all the parameters. That might be something I'd do next.
Thanks, Matt.
So in total, we identified 22 fertility anomalies and 156 mortality anomalies, which is sort of what you would expect. That fertility takes a lot longer to transition for changes than something like mortality. Like it's hard to have a one-time mortality event, where it's a little bit easier to have a one-time mortality event. So there's tends to be more baby busts. There's fewer births than there are baby booms in these time series. Mortality tends to be excess mortality as opposed to less mortality. I couldn't come up with a good term besides spike and dip. But in mortality, there was more countervailing trends where we had both positive and negative effects. So we had 600,000 anomalous deaths that occurred in both directions, whereas fertility tended to be more negative than it was positive. And these still total a very small amount of the total births and deaths in the United States over the time period. We're looking at, at the most about 1.5% of deaths being anomalous or determined as anomalous using this approach. And we looked at some of this stuff across anomaly type as well. Alaska, North Dakota, and South Dakota didn't have any detectable anomalies. New York and Massachusetts had the most. 9 states had just a single anomaly between mortality and fertility as well. You can see some of them have a lot more. Texas had a lot of mortality anomalies, additive anomalies. South Carolina had more temporary change anomalies. So I think that this sort of approach, this kind of adductive approach, it's still uncommon, but when we get large data sets, it's real easy to get significant p-values. It's pretty much always going to happen, and we begin to worry more about effect size at that point. But p-hacking still is going to continue. I don't know, maybe this is a different type of p-hacking. But this allows us to do things where we look for whether or not something is actually interesting, and whether or not something is important, and whether or not something is actually occurring. There's tons of techniques for doing this if you want to do this kind of work. Google has a tool, causal impact, synthetic cohort, difference in difference, different types of outlier analyses. Rob Hindman has a new anomaly detection method he just published like last week. But most of these rely on knowing the intervention in order to actually deploy them. So in the case of causal impact or synthetic cohort, or even difference in difference, you need to know when the treatment is applied. There was in the summer, around August, there was a paper that made a lot of waves about COVID, about the Sturgis motorcycle rally and the effect that it had on COVID rates. And they had to determine when the Sturgis effect begins. And they sort of picked a date that was, 14 days before the rally actually began. But why 14 days? Why not 7 days? Why not when the rally began? And then they had to go to an end. When does the effect actually end? This type of technique doesn't require that. The machine kind of does that on its own. It figures out when the onset and end of an effect occurs, which is kind of convenient. Modern statistical algorithms in R make this super easy. It's real flexible. And I think that the ability to look at the different types of anomalies also gives us insight into social problems for both short and long-term solutions. And I saw this quote recently that for something to be a catalyst for curiosity, and I really liked it. And I hope that this type of approach does that. I hope I mean, for me, it was very curious to run through all of them and sort of start sifting through and trying to piece together what might be driving some of these anomalies. So it's really cool to actually go forth and to explore. So I have other stuff on next steps, looking at like human mortality database data and so on for different areas, because it's really cool, and clustering the anomalies together, but I'm running long on time. So I'd welcome any kind of questions that people have, or comments,
Terrific,
suggestions.
Matt. Thank you so much. That's great. So we have a couple of questions already in chat. Let me call on just people by name. I think we have, I have queued up Ron, Dennis, Leora, and then we'll go to later questions then. So Ron, do you want to ask your question?
Okay, well, I really enjoyed this talk a lot. Thank you very much. I think all the examples we've talked about are, you might say, they're based on anomalies in an association of one outcome with another variable, which is time. That is, we're looking at sort of time trend, time series model type shifts, but we can imagine also, or can we, anomaly detection in relationships with other variables other than time. Something in relation to per capita income, or I don't know what exactly. I just wonder whether you've thought about that and whether people have tried that sort of thing for other variables besides time.
Yeah, thank you. Yeah, that's a great question. And I had a question before about space anomalies this way, spatial anomalies. So yeah, I mean, at its core, the approach is relatively straightforward, right? You're just looking for the residuals in the areas that have the greatest difference in residuals, and sort of imputing what the value should have been or would have been had you not known what it was, if we treated it as unobserved, and then estimated that value. So if you were looking for anomalies in sort of like you had said, per capita income or something like that, you're really looking for anything that's far outside of what the predicted value would have been. And the farther it is, the more you go, why is this country or why is this variable acting in this manner? And we see this all the time in different data sets. Like, this is just an approach of doing it on a lot of data relatively quickly.
Great. Dennis?
Oh, yeah, thank you for an interesting talk. I'll actually pass. I think I was just kind of trying to connect the beginning to the analysis, and I can contact you about that separately.
Okay, but maybe Robert is asking a similar question, so we'll get to the issue when Robert asks his question. So Leora?
Yeah, hi, thanks. Let me do my picture. So I was just wondering, when in your example about Connecticut, the reason for it was the stock market drop, but that's a very macro sociological, like that's all of society, and yet it's a very regional response. So I didn't quite understand why that would be the case, as opposed to, say, the whole country having a drop in fertility.
Yeah, and so on the map for the fertility level shifts, you can see that we detect a number of level shifts related to fertility in New York and Connecticut in particular is the two that were the largest in this area. I just didn't show them. Okay. We detected it as well in if I remember correctly, there was a, yeah, in Arizona was the other one. And so, yeah, I mean, I don't know. That's the other thing too, is why do we detect this in only some states after 2009 as opposed to everywhere? We would expect it to be detectable everywhere. So why didn't we? So that's one of the really cool approaches in this, or to put another way, right, is if we don't detect an effect when we should have one, why don't we detect an effect? And I don't have an answer for that. I don't know.
I mean, I can imagine something like the stock market drop might affect different kinds of industries differently. They would perceive what the future might be. And then if those industries are regional, then you might see a regional effect, but that'd be my guess.
Yeah, I'm sure we could come up with a number of reasons, right? I mean, that's what's in my opinion, what is really cool about this type of approach is that we can reason through this in a manner that's not necessarily related to, in some ways, I guess, to p-values, but not necessarily directly.
Mm-hmm. Okay, thanks.
Robert?
I was just curious, given that anomalies are defined as deviations from expectation, and that, you know, there are many ways of getting expectation. There's plenty of models and plenty of algorithms you could try. I'm curious if we should be thinking of this anomaly detection thing as anomalies being those that we can detect across a sort of variety of methods, as being sort of robust to how we're defining expectation.
Yeah. Yeah, I mean, there's multiple ways to do this. And like I said, the basic framework is the same for you know, synthetic cohort and so on. They're just different. They just require this sort of you know, the timing itself to actually implement them. Like you have to put a start of the treatment and an end of the treatment, as opposed to trying to solve what the treatment start and end might actually be.
If I could ask a follow-up, could you just put in the outputs of your sort of abductive approach into, say, one of these other approaches that requires sort of a timing? So theoretically, you know that now from your analysis.
Yeah. Yes. Right. So that would be one way, is that I could then apply any of these other methods, you know, with a start and end for a given time period, right? Because I have one. Like in the case of Katrina, it's real clear. Let's put a start and end here and see what we get when we run any of these other methods. Or you could run, it's like brute forcing it, but you can run the algorithm, you know, loop it over, iterate. So you use one time period for each one of them, right? So you're actually going through each individual time period to find it. It's rather inefficient. I'm sure somebody could come up with a more efficient way of doing it.
Okay, great. So we're out of time. Can I ask a concluding question? When you show this paper to people or you get feedback, does anybody just hate it and say that this is exactly the way we shouldn't be doing things? We shouldn't be looking at the noise. We should be looking at the signal, and this is going to lead us all on a lot of wild goose chases?
I get pushback about p hacking, right? This is a fishing expedition, is what it gets kind of viewed as sometimes. And sort of because the logic system is very different as well. And then the idea of the machine actually solving for the start and end, people are a little leery about. But it, you know, those are when I do get pushbacks, those are what it tends to be.
Great. Okay, so we're at exactly 1 o'clock. Let's turn off our mutes and thank Matt for a great talk.
Thank you. Thanks for having me. It would have been cool to have been in Berkeley at one point too.
And let me also recommend the paper. When you first put this up on the archive, I took a look at it. It was super readable, and it has a lot of deeper discussion of the things that you just touched the tip of in your talk.